Welcome, I'm Mohammed Karam Karay from Orange Research. In this part of our presentation on MIMO performance, we turn our attention to MIMO channel capacity, how to evaluate it, and how to interpret what the numbers tell us. This is joint work with my colleague Bartłomiej Błaszczyszyn from INRIA ENS. I'll do my best to keep things enjoyable, despite a few rather long mathematical formulas along the way. Instead of dwelling on them, we'll focus on what they do for us, and occasionally stop to admire their elegance. Here is how we'll proceed. We start with goals and scope, the usual promises. We then examine MIMO capacity when only the receiver knows the channel, the CSIR case, where the transmitter is, shall we say, working blind. Next, we move to the richer setting, where both ends of the link share the secret, the CSITR case. And finally, we compare the two, quantify how much that shared knowledge is worth, and conclude. Before diving in, a word on method. Throughout this presentation, plots will be our main instrument. They let us compare configurations at a glance, spot trends that formulas alone tend to obscure, and build intuition before returning to the mathematics. With that in mind, let's look at the goals and scope in a little more detail. Let me frame the motivation. This presentation is about the numerical evaluation of MIMO capacity, turning theoretical expressions into concrete numbers we can compare, visualize, and reason about. The goal is to see, in practical terms, how much MIMO systems gain from multiple spatial dimensions, and to judge how useful the available analytical results really are. We focus on two channel knowledge scenarios, both under independent Gaussian fading. In the first, only the receiver knows the channel, the CSIR case, and transmit power is spread equally across antennas, the sensible policy of someone with no information. In the second, both transmitter and receiver know the channel, the CSITR case, and power is allocated by water filling, concentrating energy where the channel is strongest. Our objectives are fourfold. We want to compare three computational methods: integration, simulation, and asymptotics, and see how they perform in practice. We want to validate the asymptotic formulas against simulation. We want to understand how capacity scales with the number of antennas at a fixed signal-to-noise ratio of 10 decibels. And finally, we want to quantify what is actually gained when the transmitter also knows the channel. One technical assumption underpins everything that follows. The fading matrix is taken to have I.I.D circularly symmetric complex Gaussian entries, the standard Rayleigh fading model. Our first stop is the simpler of the two settings, the one where the transmitter, lacking any information about the channel, has no choice but to spread its power evenly across antennas. Most of the classical MIMO results live here, and it is the natural baseline against which the value of transmitter channel knowledge will later be measured. We begin with the CSIR case. The ergodic capacity here has a standard expression due to CSITR. Essentially, it is the average, over random channel realizations, of the log determinant of a matrix that captures the effective signal power seen at the receiver, scaled by the transmit power, the number of transmit antennas, and the noise level. Unfortunately, this expectation has no simple closed form, so we must evaluate it numerically, a common fate for expressions that look tidy on paper. We'll pursue three approaches: direct numerical integration, which is exact in principle, provided the computation stays stable; Monte Carlo simulation, which is straightforward and robust, if not always quick; and an asymptotic approximation, which turns out to be both very fast and, somewhat against expectation, remarkably accurate. To evaluate the capacity by direct integration, we need one key ingredient: the probability distribution of a typical eigenvalue of the random channel matrix product. This distribution, also given by CSITR, is a weighted sum over generalized Laguerre polynomials, a classical family of orthogonal polynomials that arise naturally in random matrix theory. The precise form is shown on the slide, and the Laguerre polynomials themselves are defined through the Rodrigues formula in the lower box. Once this density is in hand, the capacity becomes a one-dimensional integral we can attempt to compute numerically. More explicitly, the three methods work as follows. The first is direct numerical integration. We integrate the logarithmic capacity function against the eigenvalue density, from 0 to infinity. The second is Monte Carlo simulation. Here we draw many independent channel realizations, typically 10,000. evaluate the log determinant expression for each, and take the average. The third is an asymptotic approximation, derived by Tulino and Verdú in the regime of large antenna arrays. It expresses the capacity as a closed-form function of just two parameters: the signal-to-noise ratio and the ratio of receive-to-transmit antennas. Let me describe what this asymptotic function looks like. It's a smooth, closed-form expression built from two logarithms and one square root term that depends only on the SNR and on the antenna aspect ratio. There are no integrals and no matrices anywhere, just arithmetic on two scalar inputs. That is what makes it so fast. A short remark on units. As written, the formula returns capacity in nats per symbol. To convert to the more familiar bits per symbol, we divide by the natural logarithm of 2. We now put the asymptotic formula to the test against Monte Carlo simulation. On this slide, the left panel shows a single receive antenna, and the right panel shows two receive antennas. In each panel, the solid lines are the simulated capacity, and the markers are the asymptotic predictions. The agreement is already remarkable, even though these are very small systems. Continuing the comparison, 4 receive antennas on the left, 8 on the right. Across the full range of signal-to-noise ratios, and for every number of transmit antennas we tested, the asymptotic formula tracks the simulation almost perfectly. That is the message we want to take away. What can we take away about accuracy? 4 observations. The asymptotic formula is highly accurate even when the number of antennas is small, which is surprising, since the word asymptotic usually suggests we need large dimensions. This accuracy holds across a wide range of signal-to-noise ratios. For a fixed number of receive antennas, the match with simulation improves quickly as we add more transmit antennas. And finally, most strikingly, the formula is accurate even for the simplest case: a single transmit antenna and a single receive antenna. Reminiscent of the Stirling approximation, famously good even for small arguments. The practical consequence is worth pausing on. With nothing more than a pocket calculator, one can evaluate the capacity of a CSIR MIMO channel. Let me quantify the speed advantage. To generate 504 evaluation points, spanning our full SNR range and all antenna configurations, Monte Carlo, with 10,000 realizations per point, takes about 80 seconds. The asymptotic formula produces the same 504 points in about 0.02 of a second. That's an acceleration factor of nearly 4,000, with essentially no loss in precision. T-table on this slide compares direct numerical integration with Monte Carlo simulation on 3 example configurations, all at 10 decibels. For small systems, both methods agree closely. For larger systems, they still agree, until the array grows large enough that direct integration fails outright, returning not a number, while simulation continues to deliver a clean result. So for large arrays, integration breaks down. Why does integration fail on large arrays? The root cause is numerical. The generalized Laguerre polynomials in the eigenvalue density oscillate more and more wildly as their order grows. These oscillations are worst near the origin, and the CSIR integral, unfortunately, starts exactly at 0. There is no way to avoid that unstable region. Monte Carlo, by contrast, doesn't touch Laguerre polynomials at all. It simply averages well-behaved log determinant values, and remains robust across all system sizes. In more detail, integration matches simulation well for 1, 2, and 4 receive antennas, with the single exception of the 64x4 case where it fails. For configurations with 8 receive antennas, it fails systematically. On timing, over our 504 points in MATLAB, Monte Carlo takes about 80 seconds, while integration, including the failed attempts, takes about 0.8 of a second. More than 100 times faster when it works. This leads to a practical strategy for CSIR. When high accuracy matters, attempt integration first, which is exact when it converges, and fall back to simulation if it fails. When low latency matters, start with the asymptotic formula, which is fast and accurate, and fall back to integration only if the asymptotic formula breaks down. The table on this slide collects CSIR capacity values, in bits per symbol, at 10 decibels, for a range of antenna configurations. A few trends are worth noting, and they will drive the analysis in the next few slides. Single antenna links deliver modest rates, as expected. Balanced square configurations reach substantially higher values, the kind of gain that first made MIMO attractive. And the most aggressive configurations, with many transmit antennas and a moderate number of receive antennas, push the rate higher still. Though, as we will see, not without limits. The plot on this slide shows the same data in graphical form: CSIR capacity against the number of transmit antennas, one curve per value of receive antennas, all at the same signal-to-noise ratio. The curves rise sharply at first, then level off. That flattening is the key feature we'll now interpret. What does this table tell us? It quantifies the payoff from adding antennas. Going from a single antenna link to a 4x4 system yields nearly a four-fold improvement in capacity. This is the combined benefit of spatial multiplexing and diversity. Multiple parallel channels, each more reliable than a single antenna link. The gains, however, are not unlimited. For a fixed number of receive antennas, adding transmit antennas helps strongly only while the two counts are comparable. Once we have far more transmitters than receivers, the curves flatten, a clear law of diminishing returns. The fundamental reason is that the number of usable spatial subchannels is bounded by the smaller of the two antenna counts. So, for CSIR MIMO, the best gains come from increasing both sides in balance. There is also an interesting asymmetry between adding transmit and adding receive antennas. Once the transmitter already has more antennas than the receiver, adding still more on the transmit side yields marginal gains, because the bottleneck is the receiver. For instance, with 4 receive antennas, a 16-fold increase in the number of transmitters delivers only a modest gain in capacity, a fraction of what it would suggest. But if instead we keep the transmitter fixed, and merely double the number of receive antennas, capacity increases substantially, by a significantly larger margin. The takeaway: in the CSIR setting, adding receive antennas typically delivers stronger peak rate gains than adding transmit antennas once we're past the balanced regime. Having charted the limits of the blind transmitter, we now ask what happens once it can see. The shift is not a minor refinement. It changes the very nature of the problem, replacing a fixed power allocation with an adaptive one, and, as we shall see, lifting some of the ceilings we just identified. We now turn to the CSITR case, the setting where the transmitter also knows the channel. With this extra knowledge, the transmitter can adapt its power allocation to each channel realization, pouring more power into favorable states and backing off in unfavorable ones. This leads to a two-dimensional water-filling strategy, spanning both the spatial dimension and the fading states, a framework established by Goldsmith, Varaya, Jayawira, and Poor. We will consider two models side by side: a theoretical CSITR ergodic capacity expressed as an integral, and a practical counterpart called quasi-stationary water filling, QSWF for short. Let me make the two models precise. The theoretical CSITR model assumes fast fading. The channel matrix changes at every channel use, and the transmitter re-optimizes its power for each realization. The coding capacity is then given by an explicit integral. The quasi-stationary water-filling model is the practical one. Here, the channel is held constant over each coherence block, typically something like 1 millisecond, and within each block the transmitter performs deterministic water-filling. The long-term capacity is the expectation of the per-block water-filling capacity, averaged over the distribution of the channel. A word on timescales. A communication block contains many channel uses, enough for the coding theorem to apply. The CSITR model treats the channel as changing within every one of those channel uses fast fading. The quasi-stationary model, on the contrary, holds it constant over the block, slow block fading. There is no a priori reason these two models should yield the same long-term capacity, and yet, as we'll see numerically, they do. This figure puts the two models side by side: the CSITR integral expression as solid lines, and the quasi-stationary water-filling simulation as markers. On this slide, one receive antenna on the left, two on the right. The curves sit essentially on top of each other. Continuing the comparison, 4 receive antennas on the left, 8 on the right. The match remains excellent throughout. The theoretical integral and the practical simulation are, for all purposes, the same. The practical consequence is substantial. Numerically, the two are indistinguishable, which means we can use the integral CSITR formulation as an accurate, efficient approximation to the practical water filling model. This is particularly useful for network-level modeling, where we need to evaluate capacity at thousands of points and cannot afford to simulate every one. There is also an important structural difference between the CSIR and CSITR integrals. The CSIR integral extends from zero, so it is forced to evaluate the oscillating eigenvalue density right at the origin, where numerical instability is worst. The CSITR integrals, by contrast, start at a strictly positive water level, determined by solving a root-finding equation that sets the total transmit power. Because this cutoff is above zero, we never have to evaluate the integrand in the unstable region. That is why CSITR integration is much more robust than CSIR integration. Water filling not only adapts the power, it also, as a side effect, shields us from numerical trouble. As in the CSIR case, three methods are available. The first is direct numerical integration. We solve a root-finding problem to locate the water level, then integrate the capacity expression from that level to infinity. The second is Monte Carlo simulation of the quasi-stationary model. We draw many random channels, apply deterministic water filling to each, and average the results. The third is an asymptotic approximation that depends on the antenna aspect ratio and the SNR. It is accurate, but only above a specific activation threshold, which we'll describe in a moment. The asymptotic CSITR formula is piecewise, with three cases depending on whether the transmitter has fewer, more, or the same number of antennas as the receiver. In each case, the capacity comes out as a combination of logarithmic and linear terms in the SNR, closed form, fast to evaluate, and scaling linearly with the receiver size. The precise expressions are on the slide. The key point is that each branch is just arithmetic, with no integrals and no random matrices. These expressions are accurate, but only when the SNR exceeds an activation threshold that we denote SNR 0. For unequal numbers of transmit and receive antennas, this threshold is a simple algebraic function of the aspect ratio, given on the slide. For square systems, where the antenna counts are equal, convergence is much slower, and we set the threshold conservatively to 20 decibels. As we'll see in the figures that follow, the approximation often remains accurate even below these thresholds. The thresholds mark where accuracy is guaranteed, not where it begins. A note on computational effort. Integration requires a nested root-finding step followed by repeated numerical integrals, moderately expensive. Simulation is conceptually heavier, but benefits from highly optimized linear algebra libraries, just random matrix generation and eigen decompositions. The benchmark for 504 points, Monte Carlo, takes about 80 seconds, direct integration only about 6. Integration wins by an order of magnitude here. This figure compares the CSITR asymptotic formula against simulation. 1 receive antenna on the left, 2 on the right. The filled circle in each panel marks the activation threshold, the SNR above which the asymptotic formula is reliable. Continuing. 4 receive antennas on the left, 8 on the right. Above the activation threshold, the asymptotic formula closely tracks the simulation across configurations. A closer look at accuracy. Deviations can appear at low SNR below the activation threshold, but they are not systematic when the two antenna counts differ. For asymmetric systems, the asymptotic formula converges to the simulation at high SNR, and the two curves merge cleanly above the threshold. For square systems, however, a small but persistent gap remains, reflecting genuinely slower convergence, which is precisely why we set the activation threshold more conservatively in the square case. Reassuringly, accuracy improves as dimensions grow. For instance, a 64x8 system is very tight. On timing, for the same 504 points, Monte Carlo takes about 80 seconds, while the asymptotic CSITR formula takes about 50 milliseconds, roughly 2,000 times faster. These asymptotics are best used within their validity regime, asymmetric configurations, and moderate to high SNR. This suggests the following practical strategy for CSITR capacity. When the system has only one transmit antenna, use the simpler CSIR capacity, because without spatial degrees of freedom at the transmitter, knowing the channel brings no benefit. For systems with 2 or more transmit antennas, when accuracy is the priority, use simulation or integration. When speed is the priority, use the asymptotic formula for asymmetric cases, and fall back to simulation or integration when the transmit and receive counts match. This table reports CSITR capacity at 10 decibels. The numbers are striking. A single transmit antenna link reaches essentially the same capacity as in the CSIR case, as we'd expect, since there is nothing to allocate across. But the capacity grows rapidly with the array size. Moderate systems already reach double-digit bits per symbol, and the most asymmetric configuration in the table approaches nearly 50 bits per symbol. A dramatic figure by any measure. Compare these to the CSIR values, and you'll see that in the asymmetric regime the differences are substantial. This figure plots CSITR capacity against the number of transmit antennas for different numbers of receive antennas at 10 decibels. The crucial visual difference from the CSIR plot: these curves do not flatten, they keep rising, even when the transmitter greatly outnumbers the receiver. A structural observation. The CSITR capacity table is symmetric. Swapping the number of transmit and receive antennas leaves the capacity unchanged. The mathematical reason is that the non-zero eigenvalues of the channel's gram matrix are the same whether viewed from the transmit side or the receive side, and the CSITR capacity depends only on these eigenvalues. A more striking observation. Unlike CSIR, CSITR continues to grow substantially even when the transmitter has far more antennas than the receiver. Take 4 receive antennas. Going from 4 to 64 transmit antennas raises the capacity from 11.54 to 29.14 bits per symbol, more than a doubling. The mechanism is power adaptation across fading states. Each additional transmit antenna increases the probability of encountering a favorable channel realization, and water filling concentrates power precisely on those favorable states. CSIR cannot do this. With no channel knowledge at the transmitter, power is spread equally, good states and bad alike. One caveat. Everything shown here is at a fixed SNR of 10 decibels. These gains are not universal. Capacity is a nonlinear function of SNR, and the story at very low or very high SNR would look different. In real networks, the relevant quantity generalizes to SINR, the signal to interference plus noise ratio, which accounts for interference from other base stations as well as noise. This quantity is itself random, shaped by user location, shadowing, and path loss. Network-level performance requires averaging capacity over the SINR distribution and accounting for traffic and resource sharing across users. That is the subject of part 2 of this series. We have studied the two regimes separately. It is time to put them side by side. Rather than read off their numbers in isolation, we will measure the advantage of transmitter channel knowledge directly, asking, configuration by configuration, how much is gained, and where that gain is worth having. To quantify the value of transmitter channel knowledge, we define a simple gain metric, the ratio of CSITR capacity to CSIR capacity, for the same antenna configuration and the same SNR. We evaluate this at 10 decibels, and summarize it in the table and plot that follow. Here is the ratio table. Look at the bottom row, corresponding to the largest transmit array. The ratio approaches nearly 3 at the smallest receive configuration, and gradually declines as the receive side grows. Though even at the balanced end of that row, the gain from transmitter knowledge remains substantial. Now look at the upper right of the table, where receive antennas exceed transmit antennas. The ratio is essentially 1. In that regime, transmitter channel knowledge brings no benefit at all. This figure shows this ratio against the number of transmit antennas, 1 curve per receive count, at 10 decibels. The ratio sits at 1 when transmit antennas are fewer than receive antennas, and then grows steadily once transmitters dominate. This figure shows the same ratio plotted against the number of transmit antennas, with 1 curve per receive count, at 10 decibels. The ratio sits at 1 when transmit antennas are fewer than receive antennas, and grows steadily once transmitters dominate. Let's interpret this. When the receiver has more antennas than the transmitter, the ratio is close to 1, no CSIT benefit, because the system is already constrained at the transmit side. When the transmitter has more antennas, however, the ratio grows substantially. A strongly asymmetric configuration with many more transmit than receive antennas can nearly double the capacity at 10 decibels. The intuition, CSITR, escapes the saturation that limits CSIR by exploiting temporal diversity and power adaptation, advantages that simply aren't available when the transmitter is blind to the channel. Let me close with an asymptotic observation. In the large array regime, when both antenna counts grow together with their ratio held fixed, the singular value distribution converges to the Marchenko-Pastur law, which is deterministic but non-trivial. The CSITR over CSIR ratio therefore admits a finite limit, and that limit is strictly greater than 1. Even when the channel spectrum becomes deterministic, water filling still extracts more capacity than equal power. The exact value of the limit follows directly from the asymptotic formulas we have just presented. Let me summarize the 5 main findings. First, the CSIR asymptotic formula is remarkably accurate and numerically stable, even for very small antenna counts, which makes it especially valuable in the regime where exact CSIR integrals become intractable. Second, CSIR capacity is fundamentally limited by the smaller of the 2 antenna counts. Beyond that point, adding transmit antennas yields diminishing returns, and adding receive antennas is often the more effective strategy. Third, CSITR capacity breaks that limit. It exploits temporal diversity to continue growing, even when transmitters greatly outnumber receivers, sometimes dramatically. Fourth, the theoretical CSITR integral closely matches the practical quasi-stationary water-filling simulation, allowing us to substitute a fast closed-form expression where simulation would be costly. And fifth, the value of channel knowledge at the transmitter is most significant, precisely when the transmitter has at least as many antennas as the receiver, which is exactly the regime where CSIR saturates. That concludes Part 1. In Part 2, we will leave the single link behind and move to the network setting, where the SNR becomes SINR. Both become random variables shaped by geometry and interference, and the question of capacity gives way to the question of network-level performance. Long mathematical formulas, I'm afraid, will still be involved, though, as today, I hope you'll find them as beautiful as they are useful. The numerical evaluations and analytical perspective presented today are drawn from our own book, Information Theory for Discrete and General Alphabets, with applications to wireless communications and networks. Its main contribution is to extend the classical information theoretic treatment from discrete alphabets to the general alphabets required by modern wireless communications. Thank you for your attention.